Okie doke, welcome back. Second video on economic growth. And we've just done the very quick intro video, what drives growth, and we found that it was technological progress, and we mentioned the Solow model briefly. And the Solow model is an example of a neoclassical growth model. So neoclassical growth models is a bigger group of models, and that's what I'm going to talk about in this video. So what are the basics about neoclassical growth models? Neoclassical growth models are workhorse models in economics. They're built around a production function plus assumptions around how capital accumulates, how technology is developed and spreads through the economy, and finally how households behave. And as I said, the Solow model is a special case. Another special case is the Ramsey model. But we're going to start with Solow. No, we're not. Let's see. Yeah, we're going to start with a production function. So, neoclassical models are built around a production function. But what is a production function? A production function is an equation relating inputs, which in a basic neoclassical model are labor and capital, to the output of the final good. And I'm giving you three examples here of general production functions. We've got, whoops, I'm off picture here, y equals ALL. So y is of course the product, L is labor inputs, and AL is labor productivity. So we've only got one input, labor. We could also have y is some function of labor with its productivity and capital with its productivity. And finally, we could also throw in natural resources. So this would be a flow of natural resources, natural resource inputs, and that would be the productivity of the natural resources. But what can we say about the variables in all these functions? Sorry, the units of the variables. What are the units of y? What are the units of L? What are the units of k? And what are the units of AK? That's what we're going to look at next. First, a little bit of theory about units. If we add together two quantities, they must be in the same units. If we have 1 unit of steel and 1 unit of apples, we can't say we have 2 units of stuff altogether. If the steel is measured in tons and the apples in kilos, we could say we have 1001 kilos of stuff or 1.001 tons of stuff. And since the same follows for subtraction, it follows that the units of quantities on either side of any equation must be the same. Any equation, okay? This isn't just economics. I mean, this is absolute basic natural science, but a lot of economists don't actually think about this. But it applies just as well in economics. Let's go back to the previous equations. So we need to come up with some units for y. So what are the units of our product, y? So this is a production function. We're not producing money, we're producing a good. Okay, so what are we going to call this good? We're going to call it a widget. Okay, this is a sort of placeholder for some kind of good. But is that the unit of y? Typically not. Typically y would be widgets per year. It's the flow of widgets coming out of our factories. Okay. Now let's assume that L, the units of L, is just workers. That's the number of workers in our factories. We could have also defined it as worker years, sort of, but we're thinking this is the worker who's working for a whole year, but we'll call it workers. Then if we're focusing on this, clearly AL must have units of widgets per worker per year. Otherwise, the units don't balance. And this is kind of nice because this is a productivity, isn't it? That's the labor force, workers, and this is the productivity of each worker, widgets per worker per year. Okay. But what are the units of K? Well, now it gets kind of interesting because it turns out that the units of K are widgets. Okay, what is going on? Well, it's kind of like this, that if we have a household here and a factory here, and this is our labor, and this is our output of widgets, some of this goes to the households in the form of consumption, and some of it goes into our stock of capital. And that is the flow of investment, isn't it? Y equals C plus I. You should all be familiar with that. And this flow of widgets into the stock of capital boosts the stock of capital, which is then the input and helps production. So the units of K are actually widgets, which means that the productivity unit must be widgets per widget per year. But these are kind of different widgets, yeah? These are produced widgets and these are capital widgets. So we could say that if you want it. Okay, and we could also look at ARR and we could say, well, or maybe I'll move, yeah. I'll just follow the notes. We then told that F must be constant returns. Why must F be constant returns, and what does this mean? Well, that red line means I'm not going to tell you. Okay, I want you to check that out and we'll talk about it when we meet to discuss the growth lectures or growth videos. Okay, so I want you to check out what this constant returns thing is all about and have a think about it. Okay. And finally, very straightforward, much more straightforward than the constant returns thing. If R is the flow of a natural resource such as iron ore, suggest units for R and AR. I want you to do that as well. Think about that before we meet. Very straightforward. Okay, so that's a bit about production functions and units. Right. And now, assumptions of the neoclassical model. So what do we assume about the production function in the neoclassical model? In the basic model, we assume that middle one, y is f of akk all, and we assume that f prime k and f prime l are both positive. What does that mean? It means that the more inputs we have, the more we can produce. Okay. But the second derivatives are negative, or less than or equal to 0. What does that mean? It means for every extra unit of a given input, holding the other input constant, for every extra unit of a given input, the extra production is less. Okay, we produce more, but the increment is less. Okay, and that kind of makes sense. That's like the hammers, right? Remember the hammers? The first hammer, it's like, wow, now I can really produce. The second hammer, it's like, oh, this isn't much use. The 100th hammer is completely useless, right? So then it would be equal to 0. And we assume constant returns as well as these. So what does that mean? Well, intuitively, it means that if you double all the inputs, you double the output, all the physical inputs, which makes total sense, right? Imagine if you build you've got a factory with a certain number of hammers and a certain number of workers, and then you build an identical factory next door with the same inputs, you're going to get the same output from the second factory. That's constant returns. But there's more to say about it. Constant returns. Okay, so that's what we assume about the production function. What do we assume about technology? We assume that it's non-rival. Okay, it's not like pizzas. Anybody can use a given technology at the same time without hindering anybody else from using it. Okay, technology is like an idea. So that is pretty uncontroversial, okay? Technologies or ideas are non-rival. But what is a bit more controversial is to say that they're non-excludable. Because in reality, if I have a great idea, well, I don't have to tell anyone, right? So that's one thing, I can keep it secret. Then I would be excluding others. I might also be able to take out a patent on it and stop other people from using it. But in the neoclassical model, we rule those things out. If you've had an idea, everybody can use it straight away. And the third thing that we do in the neoclassical model, which is even more controversial maybe, is that they just arise exogenously. There's no researchers. New ideas or productivity just increases exogenously over time. Okay, so that's technology. What about capital accumulation and consumption? Well, that's the picture I showed you just now. Here we have capital, it's being boosted by investment, but at the same time, we lose some each period through depreciation. Okay, so in a given period, we've got a stock of capital K. In the next period, we add I to it, but we lose delta K. And in discrete time, that works out as kt plus 1 equals 1 minus delta kt plus it. What would it be in continuous time? What would the equivalent expression be in continuous time? We'll talk about that next time we meet as well, or when we meet to discuss the growth. But I'll give you a clue. We want k dot, that's the start. We want k dot to be equal to something, and that's a special notation. I'm sure most of you will be familiar with it. It means dk by dt, right? Okay, so that's how capital grows. A bit depreciates and it's added to by investment. An investment plus consumption is equal to production. So there's no trade here. We can throw in trade as well, of course, but then that's just making things unnecessarily complicated at this point. Okay, and finally, so basically what I've shown you so far we assume in all neoclassical models. That is like fundamental to the neoclassical model. What about households? Oh, households are a blank page in the neoclassical model. What I mean by that is we can assume different things in different versions. And that's what the difference is. The key difference between Solow and Ramsey, for instance, is what we assume about the households, and that's coming up in the next video.